Welcome back to Reconstructing Gravity. This is Ted Cole again, and this is Chapter 17 called Solutions. And in this chapter, I'm going to present more thoughts about our constructive model of gravity and discuss some limitations, some contrast with Einstein's solution, some features, and also possibly discuss the uniqueness question. I think it's fair to say at this point that we've made some progress in describing how gravity works physically, but it might be useful at this point to contrast this approach with Einstein's general relativity approach and his solution. There were similarities between Einstein's approach and the approach I've taken here. Both processes worked from known facts to seek general principles. And one of the commonalities was that Einstein used the behavior of test particles falling in a gravitational field, and that helped him assess and analyze the behavior, the nature of space-time in a gravitational field. Whereas in our model, that those similar facts, the facts that drop balls approach each other horizontally but separate from each other vertically, that said to us that their space must be, the volume of space must be diminishing as one falls to Earth in a gravitational field. So because Einstein had removed space as a concept, those facts went into his space-time model, where for us it went into postulation about the physical behavior of space. Einstein's general relativity was a lot more comprehensive than what I've done here. The constructive model, we've looked at some common problems, the starlight bending problem, the Shapiro delay. Those were things that were used to confirm Einstein's, and we did that too. But the focus here was on gravity around a lone planet like Earth, whereas Einstein's general relativity included rotational effects, a thing called frame dragging, which we could completely ignore. And Einstein's solution was confirmed in another way by predicting correctly the non-Newtonian orbit of Mercury, which is a problem that I haven't been able to do that. It looks pretty complicated. I've only spent a little bit of time on it. Well, Einstein's general relativity model has proved to be very good, has withstood the test of time. One thing we do get from our constructive model is a physically imaginable concept, the unifying principle of maintaining harmonic cycling of energy within all particles, that all particles within a planet have the same cycling time. In our model, this defined a specific velocity profile of space within a planet such that the gradient gamma, which affects the cycling time of energy, perfectly balances the gradient strain, which represents gradient length shortening in mass particles, which such strain is produced by the internal pressure, which the same gravity causes. To achieve this balance, we found that both the pressure and the velocity of space squared, which controls gamma, inside a planet are both parabolic functions of the radius. That provides perfect balance for the strain shortening and the time slowdown caused by the speed of space. But you might recall that when I showed the solution for the speed of space inside the planet, I used the speed of space at the surface of the planet as a boundary condition for that solution. That was an essential element of ending up with that velocity of space, which is, when squared, a parabolic function of the radius inside Earth. And this velocity profile of space outside the planet was consistent with many successful gravity solutions that we did with our model. Gravitational time dilation, ball drop, starlight bending, Shapiro delay, All this stuff worked for that velocity, but this external velocity was arrived at through inductive logic, by the reason that it made those calculations worked. We trusted it. We believed in it, but is there a physical reason for this external velocity of space also? Remember, the external velocity of space which worked in all those problems was the escape velocity. And in the escape velocity, the speed of space is proportional to 1 over the square root of r. And from this we found that in order for that flow speed to be true, the flow rate, which is area times speed, the d flow rate dt had to be a constant, 12 pi gm. This was quite a puzzle at first, obviously. Unlike any other normal flow rate is normally constant, such as water flowing through pipes, such that the d flow rate dt equals 0. But here we had a diminishing flow rate. We needed a diminishing flow rate in order to maintain that escape velocity profile of the space. So I proposed that space must be doing something unusual, must be disappearing or more likely transforming, converting active light space flowing inward into passive dark space flowing outward. And that would look about like this. In the upper curve, the blue light space flowing in is converted to dark space flowing out, such that the velocity, the red arrows, are increased up to the escape velocity function. What I didn't say before when I presented these ideas is that this conversion of light space to dark space process is not inherently limited to this escape velocity profile. Other velocity profiles could be met if the d flow rate dt were a different function. For example, here's a case with less conversion, less light to dark space conversion, to get to a velocity profile proportional to 1 over r instead of 1 over the square root of r. It turns out in this case, instead of having d flow rate dt equals a constant, d flow rate dr is a constant. From inductive reasoning, this model says that the velocity of space must be equal to the escape velocity. We've got all these examples showing that must be true. But from purely deductive logic, from foundational principles, I don't really know why that's true. Speculation? Well, perhaps there's some principle of least action involved, which says that essentially nature is lazy. It takes the easiest way. I don't really know. That principle applies in a lot of places in mechanics, but I'm not sure how it could apply here, but that's just one speculation. Another line of speculation says that maybe it's the fact that d flow rate dt is independent of r. D flow rate dt equals 12 pi gm. Space doesn't need to know how far it is from a mass. It responds only locally to its adjacent space and to time itself. Certainly, though, if this were not so, then none of the Newtonian gravity equations relationships would be true. Newton's gravity equation would be wrong, and Newton's shell theorem would be incorrect. So we know it's true, but that's all inductive reasoning. That's from knowing the facts of how it works. This must be true. But from foundational principles, I'm still thinking about it. Now for a couple more quick ideas in the food for thought category. First of all these gravity concepts in our model, in Newton's model, Einstein's model, they all work if G were a different number. Newton's big G. It's the universal gravitational constant. I found nothing in my model that ties G to any other universal constant or concept. Gravity would be greater or lesser, but everything would work the same way. In my last video, I talked about random collisions of masses in space as the possible genesis of gravity. Consider, though, that gravity is typically a constant acceleration. Velocity is the rate of change of position. Acceleration is the rate of change of velocity. But there's another derivative called jerk. Jerk is the rate of change of acceleration, and certainly in collisions, there would be jerking. There would be a rate of change, an acceleration of acceleration, if you will. And I'm thinking that may be important. Engineers don't deal with jerk very much. I heard about it, but never really dealt with it because usually we're dealing about constant accelerations. But I'm guessing that jerk is a significant factor in how collisions might create a transient sense of gravity in the local space. And finally, for today, looking ahead, I want to take another look at the idea that the conversion of light space to dark space by planets and stars, together with the notion that light space and dark space always appear in equal volumes, those two facts would lead to the expansion of the universe. Last time I did this calculation, it wasn't too far off. It was a couple of years ago. And so I think I'm going to try that again and get some new data from the internet, see how it comes out. Well, that's enough for today. Thanks for your interest. Remember to like and subscribe. If you want to check out music clips on my YouTube homepage playlist tab, you'll see full-length songs of all my outro clips. So now it's time for me to find another one and say goodbye for today, and I'll catch you next time.